How to make music with an Arduino. For this project you will need an Arduino, such as an Arduino Uno, a small speaker such as the 8 ohm speaker shown here, and a resistor ideally somewhere in the 150 to 220 ohms range. You will also need to have installed the Arduino IDE. I've included a link to my How to install the Arduino IDE in Ubuntu video in the description. Before we get stuck into this project, let's quickly talk about musical structure. Music is commonly arranged as 4 beats to a bar. The beat of a piece of music is usually a regular pulse and is often played on a percussion instrument such as a drum. A musical note can be shorter or longer than an individual beat. For example, a note could span several beats, or several notes could be played between 2 beats. A so-called normal note, where the duration of the note matches the beat, is said to be a quarter note because its duration is quarter of a bar. A half note plays for twice as long as a quarter note, and a whole note plays for 4 times as long. Similarly, an eighth note would play for half as long as a quarter note, a 16th note would play for half of that again, and so on. In musical notation, each note type has its own symbol. The notes shown here are all quarter notes, but the comparative durations of some other note types are shown in red. In this project, we will use the number 4 to represent a quarter note and a 2 for a half note. Other numbers, such as a 1 for a whole note and an 8 for an eighth note, will also work. Okay, now it's time to open the Arduino IDE. I've already written out some of the code for this project. You can pause the video and copy it out yourself now, or you can download the completed code for this project using the link in the description. The first thing we'll do is define a speaker pin variable and assign the number 12 to it. This means you'll need to wire your speaker to your Arduino as shown here. If you use a different pin, simply change the value of the speaker pin variable accordingly. Next, we'll assign the number 96 to a BPM variable, which stands for beats per minute. This will establish the tempo of the music. Then we'll assign the number 10 to a note gap percentage variable. We will use this to determine how long the gap between each note will be. As shown here, the gap is expressed as a percentage of the time between 2 beats. In this diagram, the start of a beat is signified by a red line. The blue line shows how long a note of each type would play for. This is how notes would be played if the value of the note gap percentage variable was set to 25. Expressing the value as a percentage of the time between 2 beats means the gap will be a consistent length regardless of the type of note being played. Next, we have a 2D array called notes. This array contains all the notes for the music. Changing the values in this array would change the music that gets played. Each note is expressed as a pair of values. The first value in a pair is the number of a key on an 88-key piano. This diagram shows how the keys are numbered. The names of the notes are shown in blue. The yellow key is referred to as middle C. This key is highlighted in this diagram because it is often used as a reference point by beginners. The numbers across the top represent the octaves. A full octave consists of 12 keys, 7 white and 5 black. The key numbers are shown in red. These values are the ones used as the first value in any given pair of values in the notes array. So, to play middle C, we would use the number 40. The second value in a pair is the note type. As mentioned earlier, a 4 represents a quarter note and a 2 represents a half note. These are the only note types used in this music, but other values such as 1 or 8 could be used. The next 2 lines use the BPM and note gap percentage values to calculate the length of a single beat and the gap between notes. This is expressed in microseconds or millionths of a second. Now within the setup function we'll set the speaker pin as an output. Then we'll create a for loop to iterate through the notes. To obtain the size of the first dimension of our 2D array, we divide the size of the whole array by the size of the first element. We will pass each note to a function called playNote, which we will create in a moment. We will pass the key number as the first argument and the note type as the second. Now we'll create the playNote function with key number and note type as parameters. The Arduino library has a tone function, which can be used to play tones through a speaker, but the tone function cannot be used to generate tones lower than 31 Hz. An 88-key piano has a few notes which fall below this frequency, meaning we'll be unable to use the tone function in this project. To play a note through our speaker, we must repeatedly switch the speaker pin between high and low at a frequency that corresponds to the desired note. This simple technique will generate a square wave tone. As shown in this diagram, the time that it takes to complete a full high-low cycle is referred to as the period. Therefore, to obtain the amount of time that we need to set the pin high or low, we will need to half the period value. So the first thing we'll do is declare a variable called halfPeriod. We will obtain the period value from a function we will create in a moment called getPeriodForKey. We will pass the key number to this function, and since we need half of the period value, we will simply divide it by 2. Next, we will create a variable to store the length of time to play the note for. This duration will include the gap. We will call this note duration. To calculate the note duration, we will use the beat duration variable which we defined earlier. Remember that a quarter note is the same length as a single beat, so the beat duration gives us the duration of a quarter note. To calculate the duration from a note type, we simply multiply beat duration by 4 divided by the note type value. Let's quickly explore how this works. A quarter note is represented by a 4. 4 divided by 4 equals 1, so the beat duration would be multiplied by 1. This is correct as a quarter note should span 1 beat. A half note is represented by a 2. 4 divided by 2 equals 2, so the beat duration will be multiplied by 2. This is also correct as a half note should span 2 beats. An eighth note is represented by an 8. 4 divided by 8 equals 0.5, so the beat duration would be multiplied by 0.5. Again, this is correct as an eighth note should span half a beat. We also need to create a variable to keep track of the amount of time that has elapsed. We will call this elapsed and give it an initial value of 0. Now we will create a loop to oscillate the speaker pin for the desired duration. The getPeriodForKey function will return a 0 if the key number is outside the range of 1 to 88. This means we can use a number of, for example, 0 in the notes array whenever we'd like a gap in the music. As there will be no need to oscillate the speaker pin in this case, we will check that the value returned by the getPeriodForKey function is greater than 0. Secondly, we will check that the amount of elapsed time is less than the note duration minus the note gap. Inside the loop, we can use the digital write function to set the speaker pin high. Next, we need to wait for half of the period. We could use the delay microseconds function here, however, this function is unable to handle delays that are above several thousand microseconds. Therefore, we will create our own function to handle delays. We will call this function wait and pass it halfPeriod as an argument. Now we can use the digital write and wait functions again to set the speaker pin low for half of the period. Finally, we must update our elapsed variable by adding the amount of time that has passed. The last thing we must do in the play note function is take care of the note gap. After the loop has completed, we will use the wait function again. Since our loop iterates a whole period at a time, it's possible that a note could play for a fraction of a second longer than intended. This amount will not be noticeable for any individual note, but an accumulation of small errors over time could affect the timing of longer pieces of music. So whilst we could simply pass the note gap variable to the wait function here, we will instead subtract the elapsed value from note duration. This will also ensure that a gap of the correct length occurs whenever a value such as 0 is used as the key value. Now we'll create the getPeriodForKey function with key number as a parameter. The first thing we'll do is check the key number is between 1 and 88. To get the period for a key, we could use a lookup table, but it can be calculated. A lookup table would allow you to avoid having to run intensive calculations, but since we are only having to call this function once per note, the overhead should be minimal. To calculate the period, we divide 1 second by the frequency of the key to be played. Since we are working in microseconds, we must express 1 second as a microsecond value, which is 1 million. And the formula to convert a key number into a frequency is as follows. Finally, remember to return a 0 if the key number is not valid. The only thing that remains for us to do is create the wait function, which will take microseconds as a parameter. First, we will calculate the number of whole milliseconds by dividing the microsecond value by 1000 and we'll pass that to the delay function. Next, we will calculate the remainder of microseconds using the modulo operator followed by 1000 and we'll pass that to the delay microseconds function. And that completes our project. All that remains to do is save it and upload it to your Arduino.